morning, Dr. Nat here. We are doing chapter 6 part 2, which is on centripetal acceleration. Okay, so I have a picture of a hot wheel that looks like a duck, and you're wondering what on earth is going on with Dr. Nat. Okay, I have a story. So yesterday I bought this hot wheel. It's called duck and roll, right? As in rock and roll, but it's a duck. You get the idea. But anyways, I was wondering what would happen if I were to slide this duck and roll off a hill, down the hill, and it goes up again. What would happen if it was going really fast versus it going really slow? What would happen? What are the different conditions that would happen? Right? Okay, so I took this initiative and draw a picture for you guys. Okay, so this is a hill with a slope here. I'm going down the hill and up the hill again, and this is my duck and roll. It's a sunny day, it's a beautiful day, it's not raining, so we can go cycling or we can go duck and roll. So this is my duck and roll. I tried to move it at a very high velocity. Let's just say it's 100 meters per second. That's pretty fast for a hot and wheel, okay? Oh, hot and wheel, duck and roll, okay? That's pretty fast for a duck and roll because it's a toy, dude. Come on. Okay, anyways, I slide it off at v equals to 100 meters per second. What happens? It's it's going very fast, and then it's going down the slope and up the hill. What happens when it's going super fast? What will happen? Just try pushing a car toy. What will happen when it goes up again? What will happen? It flies off into space. And okay, so I had to cut short my singing, right? We don't have much time. So what would happen if my velocity was slow? Just now it was 100. Now my v equals to 10, which is kind of slow. So it goes down the hill and up again, and down again. It doesn't fly off. Why? Why do we have a different outcome when the velocity is super high versus when the velocity is super slow? So this is related to centripetal acceleration, and I will tell you why in the next few slides. Let's go. So first things first, we need to know what is centripetal acceleration. Previously, we have learned about v tangential. Okay, we have a linear velocity, which is going in a straight direction, but at each point, this v tangent keeps on changing direction. Changes direction, that is tangential to the circular path. What keeps this v tangent to keep on going in a circular motion? What makes it keep on changing directions? It's called centripetal acceleration, and the equation is AC, C for centripetal, equals to v squared, where this guy is v tangential, and r is the radius of the circular motion. So this is r. Okay, so centripetal acceleration is related to v tangential by this equation, v squared over r. So the direction of centripetal acceleration is always towards the center, like this guy. So at this point, the centripetal acceleration, AC, is pointing towards the center of the circular motion. At this point, it's pointing towards the center. At this point, it should be here, AC. At this point, it should be here. Always pointing towards the center. So AC is always pointing towards the center. So remember in chapter 3, we had equilibrium and non-equilibrium conditions. When our object had acceleration, it was in non-equilibrium condition. So for example, for this guy, I have a car moving at an acceleration of 10 in the x direction. So my F net in the x direction would be ma, right? It's not going to be a 0. It's ma because I have acceleration, which means that it is not in equilibrium, non-equilibrium condition. And how to know what are the things that goes into my equation? I would have to draw a free body diagram. So for this guy, this would be r, my normal force, and this would be my weight, and the motion is to the right, which means that my friction is to the left, right? So net in the fx equals to ma, and what are the forces acting in this direction? Would be only minus friction. So that was in chapter 3. So for this chapter, we are learning about F in the radial direction, the net of force in the radial direction. Radial means towards the center. Radial means towards the center. How do you spell that? Radial. R-A-D-I-A-L. Okay. Net in the FR is equal to, we have centripetal acceleration, which means that we have acceleration, obviously. So that becomes MAC, where C is centripetal. So MAC is centripetal acceleration times mass. So to know what goes into our equation, we would need to draw a free body diagram. So let's assume that the ball is weightless for now. Okay, so if this guy didn't have any weight, what are the forces other than weight acting on here? I have a string, which means that I would have tension, right? Whenever I have a string, I would have tension. And do I have a normal force? No, I do not, because I am not on a surface. So the only force in the radial direction or acting towards the center is just tension, right? So now my equation becomes T equals to MAC, or I could say mv squared over r, where v is the tangential velocity and r is the radius. What is the radius? The radius is just the radius of the circle. If it's 10 meter, then it's 10 meter. Don't put in the diameter. Okay, so that is a little bit on the equation. Centripetal force changes the direction of velocity. Okay, remember that we have AC, which is equal to v squared over r. FC, centripetal force, is just MAC. So the force should act in the same direction as the acceleration, which is towards the center. So centripetal force changes the direction of velocity. Remember, we had tangential velocity where it was going in a straight line, but it keeps on changing direction. This is because we have force that forces the tangential velocity to keep on going towards the center. So that is why it keeps on moving closer towards the center, so eventually it goes in a circular path. If centripetal force vanished, which means that there's no longer a force acting towards the center, at this point the V tangential would force the ball to go in a straight direction. So the ball goes up instead of going in a circular motion. So again, if the force vanished, the ball, let's say the string snapped over here, which means that there is no longer a force that is pulling the ball towards the center, right? So the ball, instead of going in a circular path, it will go in the direction of tangential velocity, which in this case, upwards. If the string snapped over here, right? Snap. The ball would fly off here. Going down. Okay, so back to our duck and roll example. So why do I feel like I'm gonna fall off at point B and not at point A if I'm going really fast? Where is the centripetal acceleration in this problem? Okay, so for you to see how this is going, let's use purple color. So here, when we are going down the hill, the centripetal acceleration is acting here towards the center. This is my FC or my AC. Let's just put AC there. This is my AC. And in this condition where I'm at point B, my centripetal acceleration is going down, AC. So how does that influence what I'm feeling differently? So let's write the equation. Okay, so to understand what happens at point A and point B, I would have to draw my free body diagram. Always draw your free body diagram, guys. Don't be lazy because it's going to help you. So at point A, let me just label this point A, and this guy would be at point B. Okay, and this is my normal force. Normal is always perpendicular to the surface, and that is my reaction force or normal force. I have weight. My duck and roll has weight. I don't know how many grams that is. I think it's 58 grams. Okay, so I've drawn the reaction force and weight for both of my duck and roll at these two positions. So now I would like to know where is my centripetal acceleration. So centripetal acceleration always points towards the center. So this is my center and this is my center. Okay, so this is my center. So centripetal acceleration goes in this direction. That is AC. And for this position A, my centripetal acceleration is towards the top. Okay, so now I have two different conditions and two different equations. So now let's write the equation in the radial direction. So net force in the radial direction is written as this guy, net F, capital F, R, which is radial. So I know that I have centripetal acceleration because it's we are in a half circular motion. So this equation becomes MAC. Okay, where is my positive direction? My positive direction is always in the same direction as my AC. So let's say if my AC is going down, so that is my positive direction. If my AC is going up, that is my positive direction. So for A situation or A position, MAC, so R is in the same direction as AC, so R becomes a positive. W is in the opposite direction as AC, so that becomes a negative. So my equation now becomes R minus W, weight, equals to MAC, or mv squared over R. Okay, so that is for A. For B, what is the force acting in the radial direction? It's MAC. I have the mass of the duck and roll and I have centripetal acceleration. And this is equal to positive weight because weight is in the same direction as AC. And my reaction force is in the opposite direction. So my equation now becomes MAC equals to weight minus R, or mv squared over R equals to W minus R. Okay, so here if I were to rewrite this to have my R as my subject, so this becomes mv squared over R plus mg is my weight, right? So I put this negative weight on the other side, becomes positive weight, which is just positive mg. Okay, so now let's take a look at what happens to the R for B. So R for B is just mg minus mv squared over R. Okay, but given this equation, this doesn't explain why my duck and roll wants to fly off at point B. Why does it want to fly off at point B and not at point A when I'm going really, really fast? Okay, so if my V is super fast, my R, let's just see, when V is super fast, my R becomes super heavy. My R is super large as well. When V is super fast, my R is also gonna be increasing, right? That means my duck and roll is gonna feel super heavy at point A when the velocity is super high. Okay, when R is super large, gonna feel heavy because that is the perceived weight. Okay, Okay, so R becomes super heavy. What happens when our V is super fast and we reach point B? Sorry, that was my son. So let's see. When V is super large. Yeah, V is super large. What happens? R can become. Yeah, R. R becomes smaller. Or it can be 0. It can also be negative, right? So when R is smaller, the duck and roll feels lighter. Just now it felt heavy, right? Duck and roll was super heavy. Now it feels lighter when it reaches point B. So when R becomes 0, it has reached the maximum velocity to which it can still maintain contact. It can still maintain contact. Okay, so if R equals to 0 is the limit to which the duck and roll can maintain contact with the hill, what happens when R becomes negative? Duck and roll flies off. So R cannot be negative. Why? Because R is a normal force, and the condition to have a normal force is that contact must always be there. If there is no contact, there is no R. So R cannot ever be negative. But this is a calculation. So sometimes we get into a problem where the value becomes negative. It just means that R is not there. It flies off. It's not in contact with the hill. Let's summarize what we have learned so far. R increases when V increases, right? R decreases when V increases at point B. So when our normal force is super large, duck and roll feels heavy. When the normal force is super small, duck and roll feels light. When R equals to 0, this is where duck and roll achieves. Achieves the maximum velocity is achieved. And when R is negative, not possible, which means that duck and roll has flew off to the moon. The end. So I'm guessing you can figure it out what happens when V is super small. So try that out yourself and see if you understand. Okay, so that's it from me for part 2. I'll see you for part 3. See ya!